ajspeller.com. In today's tutorial, we're going to use technology to verify and model the results of a related rates problem. Here we have the radius r of a circle is increasing at a rate of 3 centimeters per minute. We need to find the rate of change of the area when the radius is 6 centimeters, 12 centimeters, and 24 centimeters. Here you see all the work that we've already done analytically. So what we're going to do now is we're going to change this problem into a parametric equation. So we started off with the equation for area of a circle, where we're saying that the A is equal to pi r squared, and we also know that the change in rate, the change in the radius over time, we know that there was 3 centimeters per minute. So what we're going to do is we're going to take the variable r and we're going to set that equal to t, but we need to keep in mind that that radius is changing at a rate of 3 units per minute. So to do that, it's understood that a 1 is sitting here saying that for each time unit the radius is changing 1 unit. We want it to be 3 units, so instead of a 1 there, we're going to change that to a 3 because of what we have here. So for each time unit, that radius is changing 3 units. Now we're going to do a substitution. We're going to substitute 3t back into this original equation for the letter r. So here we end up with a is equal to pi times 3t squared, because the radius is now symbolized by 3t. And the next thing I want to do is I want to take the implicit differentiation of the area with respect to time. So here we have dA dt. We're going to keep the constant pi. We have to use the chain rule because of what we have inside here. So first the power rule, bring the 2 down forward, rewrite the 3t. We decrement the power to 1, so it's understood to be 1, so we don't need to write it. And then we take the derivative of the inside. Well, the derivative of 3t is just 3. So this here is the expression that now represents the change in area over time, and we're going to incorporate all of this information into our model. So let's go over to the model. Let's begin by putting in the radius. So we have a slider for the radius called r. I'm going to have that radius go anywhere from 0 up to 25, moving in steps of a tenth. Next, let's put in the dr dt, or the rate at which the radius is changing. We're going to call that d, again giving it an initial value of 0, but then changing the boundaries. It can go from as low as 0, I'm going to say as high as 10, and again moving in increments of a tenth. And last but not least, we're going to put in a slider for time, again with an initial value of 0, but we're going to change the boundary so the time goes from 0, and I'll say up to 20, and I'll also give that a step of a tenth. Next thing I want to do is put in the equation for a circle. So let's go back and let's talk about that. So if we want to put in the equation for a circle, we know that that equation is x squared plus y squared is equal to r squared. But in our problem here, we're saying that r is 3t, so we're going to rewrite that as x squared plus y squared is equal to 3t squared. Just doing a basic substitution. And one extra thing we're going to do just for the model is we're going to change this into an inequality. We want the inside of the circle to be shaded, so we're going to change this equation to x squared plus y squared is less than or equal to 3t, the quantity 3t squared, because that's going to allow us to shade the inside of that circle. So let's put that equation into our model here. So we have x squared plus y squared is equal to 3t, and that quantity is squared. Alright, we don't see anything at this point because we said we have the t at 0. So what we're going to do is we're going to increment the t, and there you see we have a circle that's being drawn in. And let me add in that less than or equal to. So now we see that the inside of that is shaded in, so it helps us to better visualize the model. Next thing I want to do is let's go ahead and change the color. So let's make this thing red. And next let's put in the radius. So to do the radius, let's put in y equals 0, and you see that draws a horizontal line on the x-axis. We want to limit the values of the x-axis to go from the origin to the outer limit of the circle, which is going to be one of these x values. So to do that, we do a curly brace. we want to start at 0, less than or equal to x because we're on the x-axis, less than or equal to the radius because we're going to go from the center out to the edge of the circle. That's going to be the radius, and we said the radius is symbolized by the expression 3t. And when we do that, the radius is drawn in, but let's make that black to make that a little bit more easily seen. So there we have the radius drawn in, and again, as we move the time, we see that the radius also moves with the circle. All right, the next thing I want to do is I want to put in the equation that we came up with that represents the change in area over time, and let's just go back to take a look at that again. That Let me put a square around that. This here is the equation that we want to put in. We're just going to put in the expression though. So pi times 2 times 3t times 3. So let's go back, and that's pi times, what did I say it was? Let me go back again. Times 2 times 3t times 2 times 3t times 3. All right, and now let's go ahead and set this equal to 6, because in our problem up here we found that when the radius is 6, we found 3 pi centimeters squared per minute to be the rate at which the area is changing. So let's put that in place. Let's change this radius up here to, well, actually, you know what we need to do? We need to actually put in an expression so that we know what that radius is. So, well, there are two things we can do. We can set the radius here to 6, and then once it's at 6, we can move the time so that it's right over that. Or what we could do is we could put in, the radius is 3 times t, so we can just write in 3t here. And once we move this around, when we see that this value here is at 6, then we know to stop. So I can come back, and when it comes down to 6, I know that I'm exactly on top of that radius at 6, and then I have a decimal equivalent of the area. We said the area was 36 pi, so let's type in 36 pi and see if those are equivalent, and we see that they are equivalent. The next one, radius that we were going to set everything at, was 12. So when I move this up to 12, I see that it's much larger, so I'm going to have to change my view here. So let's just zoom out. And now let's move the t value over until we see a 12 here. So we move this over. All right, here I am at 12. I see I have the 226, decimal point 1946, etc. Let's go back to our analytics. We see that when r is 12, the area is changing at 72 pi centimeters squared per minute. So let's type in 72 pi. So down here we put in the 72 pi, and we see that these two values do match exactly. And let's do our last one where the radius was 24. So let's zoom out some more. Let's set this radius all the way over here to 24. And now let's move the time over till we see our expression here is at 24. Alright, and if I remember correctly, when r is 24, we see that pi should be 144. So let's set this here to 144, and we see that these two here are matching exactly. Alright, one other thing that I want to note here to make this problem more dynamic is we want to use this slider D. Right now I'm not incorporating D at all. So what we need to do is let's go ahead and set D to the rate of change of the radius, and for this problem it was set to 3. And now what I want to do is for everywhere that I see the radius, it has a value of 3, I want to set that to the value of D. So that becomes dt. This here also becomes, for the radius, becomes dt. When I come down here and actually work on the expression for the rate at which the area is changing, this 3 here becomes a D. And because I used the chain rule to get this 3 here, this 3 here also has to become a D. And again, that's from when I used the chain rule here to take the derivative of this 3t to get this 3. I have to change this 3 into a variable because that symbolizes the change in rate over time of the radius. So that's why that 3 there also became a D. And then this 3 here is also going to become a D. And now if I go back and now if I move this D around, you see that this here is going to also dynamically impact what we're doing in this problem. All right, that sums it up for this tutorial by ajspeller.com. And as always, thank you for watching.